Good evening, everyone. On behalf of the Kuwait Foundation for the Advancement of Sciences, it gives me great pleasure to welcome you all to this KFAS speaker event. Our goal is to transform Kuwait into a knowledge-based economy, and we strive to do this through the promotion of science, technology, and innovation. This evening, we have arranged to have a special guest join us to share his insight and expertise. Professor Ikhlaq Sihu is the Chief Scientist and Founding Director of UC Berkeley's Saturdja Center for Entrepreneurship and Technology. In this forum, Professor Ikhlaq aims to help us understand how data and AI relate to workflow. Without further ado, please join me in welcoming him.
Okay. Welcome, everyone. Let's see. Is it welcome to me or welcome to you? I'm not sure. I'm very happy to be here, and this is my first time to Kuwait. I'm excited actually to be here, and what I will talk about here. There's three parts to what I was going to share with you. One part is I just need to tell you a little bit about what I do every day, okay? That's not the interesting part, okay? But you just need a little bit of context. One part is what's happening with data, with AI, artificial intelligence, kind of a little bit about where we've been, what's around the corner in terms of research, what some of the applications are, how some of these things work, and then the third part is what does this mean for jobs? What does it mean for employment? Because these things are related with each other. And hopefully that's what you think that I'm going to talk about also. Anyway, that is what I'm going to talk about. So let me go ahead and do that. Take some questions more at the end. But if you need anything clarified, or you just, if you want to say, did you mean this or that, or you want to talk in the middle, I'm perfectly okay with that as well. Okay. I have a lot of microphones here. Yeah, okay. All right. So let me put the slides up. Just hold on. All right, these are mine. Right. Okay. So hopefully artificial intelligence and data are things that you're interested in. And so that's basically what I'm going to talk about. Before I do that, I'll just mention a couple of things. One, I am visiting from UC Berkeley. That's where I spend basically all my other days, at Berkeley, except when I'm not in a plane. And about 14 years ago, I started something called the Saturdja Center for Entrepreneurship and Technology. And this is a center within the College of Engineering at Berkeley. In these 14 years or so, it went from being basically me, one person, trying to make something work at Berkeley, to a fairly large part of the College of Engineering. It's a kind of an institution on that campus. 2015, 3 years ago, we received an endowment gift, a large gift from the founders of Marvell Corporation, and it went from being Center for Entrepreneurship and Technology to Saturdja Center. So it's a permanent part of the Berkeley campus. It won't go away even after I leave or whatever. It would continue on, and like I said, it's really an important part of the college. The way and I don't want to go too much into this, but the way it got started is that the advisory board of the College of Engineering used to tell our dean that engineering needs to be broader, it needs to be wider, that there's kind of a narrow version of engineering to be able to solve a problem, and then there's a broader version where people would know what is the problem to be solved. They would be earlier, they would be later, they would interact with a wider, that's not me, right? Yeah, okay, all right. So they would basically being able to start something start a venture is not simply solving one problem. It's a much more holistic, broader view of engineering. So this center was started because of that, to broaden engineering. And today we have about 1,500 undergraduates that take courses in our center. I have executive programs. I see executives from Google, Yahoo, Network Appliances, Samsung, Cisco, all the major corporations. They come to our center, and it's actually something amazing when companies like Apple come to you and work on their innovation skills. So it's something I can feel good about that, actually, right? Because normally you would think you would go to Apple to learn how to innovate. So anyway, we're in a very good ecosystem. We do a lot with our X Labs, that's in areas of data and AI and blockchain. And actually we have global partners all over the world. Okay, I'm trying to keep the intro part short so I can talk about the other things, but I do want to tell you something just about the way we teach people. And I think this is worth understanding. It's not so much for the introduction, but I think it's worth understanding itself. So remember, we started off teaching people how to be broader, how to do more, right? Not be narrow in their engineering capability. So this chart basically explains an idea. And the idea is that everybody in this room, all our students, me, everyone, you could put them somewhere on this chart. And the y-axis, the vertical part of this chart, is how good are you in a skill area. Like how good are you in computer science or in finance or whatever you come to a university for, the degree, the subject that you study, how good are you in that way, okay? And now the other axis, the x-axis, this broad one, this is how good is your psychology towards innovation, like how you interact with people, how well do you actually hear what they're saying, how good are you at getting them to help you with things. It's kind of like being street smart. There's a whole bunch of skills that have to do with this broader part of education. Typically what happens, people who are very smart and they go to great schools, they're very good on this axis and they tend to be a little bit narrow on the other one. And then they go to work and they go to companies and other organizations, and they're full, there's whole groups of people who are really smart on that vertical axis, and they're all still a little narrow. Not so many are very far out on the other one, okay? And a number of you are nodding your heads, meaning you know exactly what I'm talking about. And you know what happens when you get a person who's just a little bit broader than everybody else in the company? Like they're all smart, but just a little bit broader, you know what happens? They become the vice president, right? They become promoted. They become the leader, not because they're the smartest person, not because they're better in the skill than every other person in the company. They're about good. They're like other people here, but they're actually broader in this other way, and that sets them apart. And if you go farther and farther out, and you get kind of really good in both dimensions, that's what we think of as like the great innovators, like Steve Jobs or whoever you might think of. It's people who are strong in both these capabilities. So what we're doing, and I know this talk is not about this talk is going to be about AI and data and things like that. But what we're doing, what we've been doing for a long time, is we've been taking our students at Berkeley and we've been pushing them farther and farther, as far out as you can in this other dimension. In other words, all the rest of the university is to get you to be better in the vertical dimension. But what we're doing is taking those people and stretching them in this other way. I could give you an entire talk on all the ways that you can push people to do this. It's basically like sending people through a psychological therapy so that they can have wider comfort zones, so that they can use inductive learning, so they can, have all these capabilities. But I won't do that. I just want to tell you this is what we do. This is one thing that we do. Now, we have a way of doing it, which I also won't explain, but we have a way of doing it, and we have success with it, meaning this is like a resume of the center. I have many, many student companies that, they start something and they sell to Facebook for $100 million, or they, like they graduate and within a year or two they start something and it becomes successful. And so anyway, lots of things have started from the center. And so all of this is really, so you know, part of the context, part of like the environment that I'm coming from and that I'm talking about. There's actually another part of my background which I think is worth communicating. So all my degrees are electrical engineering through my PhD. And one thing that I have worked on in the more recent 3 or 4 years, and I have actually a very extensive. I'm one of those very narrow, deep people. Basically, that's what I'm saying. I'm not actually supposed to be one of the broad, wider people. So I have a very detailed, technical, long history of doing technical work. And in the last 3 or 4 years, even though I've been working a lot on pushing people in the psychological broad dimension, I've been focusing more and more on what we can do with data and artificial intelligence and some of the technical topics. And about 2 years ago, maybe it's a little longer now, 2.5, for some reason, I just got it in my head that it was time to redesign a data science class. Like from scratch, what would you do? Like what could I do to kind of reinvent how we teach data science? And I said, okay, well, maybe I could create the course that I wish I could take, right? Like, and frankly, a lot had changed since I had gone through my technical education and even all of the technical work that I've done. This field has moved quickly. And so I'm like, what would I actually want from a class like that? And I said, basically, I would want it to be something so practical that you could really just build anything that you want if you took this one class. I wouldn't want it to be just theoretical. I would say you should learn all of the tools, basically the same machine learning stack, the same software tools that is used in every company, that everyone who creates, who innovates, they use these tools. They're all free anyway. To use those tools to still have the math theory, but to have a project which is completely open-ended, nothing fake. Like you come into the class and you say, I want to create something that can predict that this article is fake news, or I want to predict where I should walk to avoid crime. You pick any project you want that has some statistical property to it, some machine learning in it, some artificial intelligence, and you should be able to do it. And I remember that when we first started to offer this course, people would make up projects that they did not even believe that they could do. And about halfway through the class, they discovered these tools are so powerful that they could actually do it. Like they didn't know they could do it, and we were teaching them all the components, and then by the end, they're actually doing this. By now, we've been teaching the class we've taught it for 4 semesters now, and the enrollment went from 55 to 90 to 135. This semester it's 220, I think, approximately. And we're trying to, we could make it as big as we wanted, as it could get bigger. We're capping it. We're trying not to get it to be bigger than that because we want to actually spend some time talking to them. Like if it gets too big, can't talk to anyone individually anymore. But we've had a lot of success with this, and we've been and people have been interested in like short versions, executive versions all over the world, in Hong Kong and Prague and here, and just so this has been going on, and this is also part of the background. Okay, now let me tell you a little bit about data AI. All right, so first, this is a really basic piece of information about how data AI kind of works. And what it says is that usually you always start with a table of data. Okay, so this black box, I don't know if you can see it, the box on this side, right, the one that says extracted data, often in table format, that's supposed to be a table of data. Usually these tables are really long, deep tables. So like you can have a table that has 1,000,000 rows in it or 100 million rows in it. It might have 20 or 30 columns, but you could list every person in the United States, or you could list all the, any product, whatever. Every row is something that you would want to keep track of. And then the columns are usually what you call features. I'm not trying to go into all the detail of it, but basically you get data in a certain format, and people do two things with it. They take that thing and they will guess metrics they'll predict metrics that you don't know for sure, but you want to make a guess what they are. So do you want to know somebody's credit score? If you want to know, you want to guess how they're going to score on an exam. You want any number of things that you could be making a prediction. That's one thing that you do with machine learning. The other thing that you do is you take the data in that table and you consider them like points in a space, and then you can divide that space. So you can say which are the rows that are a picture of a dog and which are the rows that are the picture of a cat, or which is a sound and another sound, or you can recognize anything that you can separate or classify. That's the other thing that people do. So either you're doing a prediction, you're guessing a number, or you're separating and you're automatically dividing data into different parts. Is that clear? You're hearing, you understand? Am I being clear enough is really the question. Okay, so let's suppose that these were all people who were watching, or are customers of Netflix. Then if you wanted to recommend a movie to one customer, then the dots that are the closest to the one that you're looking at, if you want to recommend a movie to somebody, what you would do is you would look at the dots that are very close to that one. You'd say, those people are most similar to that one person that you want to recommend. Whatever movies they seem to like a lot, that's what you probably would recommend to this person, right? You can kind of see the basis of a recommendation engine from this idea in classification. And so what I just explained to you is what happened in the 10 years from about 2000 to 2010. And in that decade, all of the examples that you think of in terms of machine learning and AI, they are roughly like this. So when you go to a website, it says people who bought this also like this, that's an example. Or when you go to Match.com, and I'm not saying you're going to Match.com, but when someone goes to Match.com and then they recommend, oh, this person would be a good match for you, it's the same. It's an algorithm that's doing a recommendation. By the way, those algorithms, they're very interesting. Some of them are matching on you should marry someone who's very similar to you. And the other version of the algorithms, there's a different company, eHarmony in the United States, they match on how different they are from you because they're looking for complementary instead of two same. So machine learning doesn't actually solve all the problems. You still have to kind of decide what protocol, what you're really looking for. But you're taking the data and you're seeing, what's next to each other, and you're making predictions. This employee is more likely to be a long-term good employee. All examples of the same idea, right? It's basically this. Okay, then, so that gets you to 2010. A little bit into this, about 2014 or 15, something really changed in the way that we started to do predictions and classification. And that's what this graph is intended to show you. So the way that you think of it is that big table that I showed you, the black box, you just call it X. And that's literally how you do it in the code also. It's just X. And, by the way, like in code, X used to be like the number 5, like an integer. Today, X is a table with 1,000,000 rows. It's nothing like it used to be. Coding is not, X is an object. It's a name object. The object, you can say X.sort and sort the whole thing. It's a very, very different world, okay, than when I grew up. Anyway, so you put in X, and you get out the labels Y. Like the labels would be, is this a cat or a dog? You get a number, like this is your credit score. So you put in something, and you get something out. You get the prediction out. So we used to have a whole bunch of very well thought out algorithms that would partition or predict the data. And then what happened is that someone said, okay, don't worry about having such a smart algorithm. Why don't we just have an approximation for every function that you could possibly have? So that's what a neural network is. You put in X, and it takes all these numbers and it multiplies them by weights, and it goes through a bunch of layers, and out the other end comes another set of numbers. That's it. So it's a function, and all the weights will determine what that function actually is, right? So if it's a very deep set of layers, that becomes a deep learning network, deep neural network. If it's just a few layers, it's just your normal neural network. Anyway, just think of it as another function. Don't think of it as anything more than that. Just put in a number, you get another number out, okay? So what happened is, like, you can basically put in an image into the front of one of these networks, and out the other end, you will get a few outputs, and it could say the output is, this is a picture of a dog, and the other output could say, this is a picture of a cat, and this is a picture of a zebra. So you put in a different image, you're going to get a different output. It'll classify for you. In 2014, there was a breakthrough, which was that the neural network version of this outperformed all the other algorithms, right? The first time neural network basically beat all the other algorithms. So there's a very famous, what is it, a competition, very famous competition that runs every year. And there's 1,000 different types of pictures, like ball, plane, train, baby, all these pictures. And the job is you train it, you give it lots of pictures which have labels, then they give it pictures which you've never seen, and it has to guess which of 1,000 different pictures is this one. So in 2010, the error rate was 28%, so 72% of the time it was guessing the right picture. One out of those 1,000, it was guessing the right one. Okay, and that's been dropping. In 2014, the error rate was 7%. This is getting very close to human capability. Like, we cannot guess much better than 5-7%. In the most recent year, it's something like 3%. So the computer's ability to classify is now better than our ability as humans, right? So this, we kind of crossed that point. And we basically did it with this neural network type of algorithm. Now, I will say neural network doesn't actually work better in all situations. It requires a tremendous amount of data to train it with. But in this situation, what happened is it became better. And since then, almost everyone does classification and prediction with neural networks. As long as they have data, that's what they're doing. All right. So from there was another kind of issue that happened, and that's fine. We can predict, like we can classify, we can say, oh, that's an image, or we can predict a credit score. We can do all of that, but that does not solve the problem of what if you have a sequence of moves? What if you have a sequence of steps? So like if you're teaching a robot to walk, then it's like you have to, like every joint, you have to say, now move this finger, now lift your leg. It's not just recognizing one image. It's from this state, what do you do next? And from that state, what do you do next? And from that state, what do you do next? And the normal way that, like the simplest thing that you could do is you could try programming these steps. You could say, do this and this and this and this. If you get more sophisticated, you could say, well, how heavy is the arm? How heavy is the leg? Let me characterize it so I know if I put in this function, then I expect the leg to work in this way, right? So you can get better and better. This would be basically using control theory to make your walking program better. All right, so in 2015, this is basically, sorry, that song doesn't really help, but you get the point that there's not quite a perfect way of like getting robots to walk. And this is at Stanford, and it's a DARPA challenge. So all the other, very good schools are there, and the students have been working on these for a long time, and you just have robots basically falling down regularly. Okay, so it turns out there's another way that you can try to teach a robot to take steps or, solve the same problem. And it's a very clever way, okay? The way is that you're going to actually just let the robot make all random moves. Every joint, you just randomly let it do every joint. It's going to make some random motion, okay? But there's two variables that you're going to pay attention to. One is how high is the head, and the other variable is how quickly is it moving in one particular direction. So the robot makes some random move, and if the head ends up a little higher, you remember the sequence of things that got the head to be higher, and you reinforce that. So the next time you're in this state, you're more likely to do the same thing that got your head to be higher. And if you randomly did something that you moved in one direction, then you would, again, reinforce more likely to take that step again, right? So there's not actually any programming of what the robot is going to do. There's just reinforce what seems to be closer to your objective function, what you want it to do. By the way, that's exactly how children learn to walk also. They don't know how heavy are their arms. They don't have a program in their head about how to walk. No one directs them, now do this and now do this. They just do random things, and then some things make them happy. That would be the objective function. So your head being higher up makes you happy. Being able to move to another place makes you happy. So you do these random things, and eventually you learn to walk. You fall down a few times, but you learn to walk. So they've been working on that. This is called reinforcement learning. And Peter Beal, who's in this video, who first did this work at Stanford, and now he's at Berkeley, and he's very much a proponent of this type of machine learning. So here's an example.
Here's what you get.
And
initially, the robot is essentially
here, I'm going to turn his voice down. I think you can kind of get the idea. Do you see? All right, that's 160 attempts of randomness, and it's getting better. 320 there. Let's see, on the next one, 640 trials. So it's almost running here, right? Like there's no program. It learned how to move its arms. It learned that if you put your leg here, then a good next thing would be to put your leg there. And it's keeping some sort of balance all in the process, right?
Now the beauty here is that if you swap
Okay, and I'll stop this here. But what he's saying is that then you can take that same algorithm and you can put it. Do you still hear me? Okay. There's more mics here. So, okay. So what he's saying is that you can put the same algorithm into another robot that has 4 legs and doesn't have anything to do with the last one, and it will work there also. It has nothing to do with 2 legs or those arms. It doesn't have to do with the fact that you're supposed to have the arms in the air and the feet on the ground. Like whatever configuration you put it in, that algorithm will learn how to keep the head up and how to move forward. Okay, so again, this is called reinforcement learning. Perhaps you've heard the term. It's basically what it is. And this is the very same algorithm. So just like if you want to take a set of moves, if you want to play a game, you're also doing a set of moves. So if you're in this state, which move would most likely get you to a victory? You reinforce it. The way it works, obviously, what happened with AlphaGo is that the world's champion in the game is beaten by the computer, right? So the way that happens is the computer plays another computer, and in some short time, a few months, it can play hundreds of millions of games. It could probably play more games than all humans ever have played in that game. It can reinforce, basically, it can learn, it can reinforce the best pattern of moves, and a few heuristics are applied. Like at the very end, if you're only 2 moves or 3 moves away from a victory, that can get programmed in. Like once you get to this spot, then logically do this and do this and do that, something like that. So it just plays itself for a while, reinforces the right moves, and then you can have it play a human who's very good at it, and basically it wins, okay? So that brings you to this question, which is, does that mean that AI can do everything better than humans? What do you think? The answer is, of course, no. It would be a really terrible talk if that was the message. Although there are people who give that kind of a talk. I don't know what's wrong with them. But anyway, I don't think that's true. Actually, I don't think we in general, as a university or like researchers, believe that to be true. So one thing to understand is that the game here is a very different problem than real life. So the game is much more simplified. There's discrete steps. You're only playing one player, that's single agent. All the rules are known, that's fully observable. And the objective is in a certain number of steps, that's finite. Real life is the opposite of all of those. There's a continuum of, like every 10th of a second, every 100th of a second, down to all time horizons are part of the set of moves that you can make. It's multi-agent. You're considering every single other person as part of what you have to react to. It's uncertain, meaning, in a game, if you do one thing, you're going to get a response. It's predictable. In real life, you talk to someone and their mood is different than on a different day, you get a different response. So there's like randomness built into everything that happens in real life. And then, of course, the time horizon is infinite. I should point out that you can kind of be fooled a little bit by machine learning in the sense that it's kind of like you see a calculator and a person and you ask them to compete with each other and you say, all right, multiply this 5-digit number with an 8-digit number, and you say, who's going to win? Of course, the calculator is going to give you an answer faster. But that's because, again, the problem is really, really narrow. Okay, so in that very narrow situation, the computer will always win over the human. But if you give it a broader question, the calculator cannot beat the human. And that's still true with machine learning, and it's not obvious, right? So if I take a child and I show them an apple one time, like, look at this, this is an apple. And I put it away. And then I don't show them that fruit for 3 weeks, maybe, and they see all kinds of other things. And then I say, what's this? They'll say, that's an apple, right? Do you know how many images you have to show an algorithm before it can recognize an apple? Right? Like literally what is it, 100,000 or something? The algorithms are nowhere near as efficient as people's brains. Okay, so just because we can get it to do something that seems like it's human, we're a long, long way off, and the problems that humans deal with are much, much more complex. So first, I want to dispel this thing. It's not that calculators or machine learning can do everything that humans can do. Okay. The other thing is humans and the way machine learning really works is that it basically just picks up signals of what people are doing, and then it amplifies patterns that it observes. If you take away the input that people provide the algorithm, the machine doesn't have anything to learn from. In fact, it starts to basically forget, or it starts to like lose its capability. It requires observing people in order to even work. So I'll give you this example with Google. You can say that Google is like artificial intelligence. You type something in, and immediately you get a whole bunch of responses that are very relevant. So, you ask it a question, it'll say, here's one, here's a restaurant you might try, whatever. The reason why it's so accurate, well, let's take a look at what's going on. First of all, it's ingesting millions of web pages that people have written. Okay? Didn't figure out any of that itself. These are all data that people have written, and it comes into Google. Inside Google, there are people who are fine-tuning the way the presentation is given to you. So if you typed the name of a restaurant, it will know to tell you this restaurant is closed right now. It gives you information that you didn't ask for. That was not automatically generated by machine code. That was logically written in there. If they're looking for a restaurant, we should give the time of whether they're open or not. The people have decided how to parse and present this information to you. And they're changing that all the time. They work at Google. And then you get these results, and people click on different things, and those clicks go back to Google. And that's also part of the learning. So if you even just took away the feedback clicks back to Google, Google would stop working well, because Google would not know what is a good response from a bad response of all the random things that it gives you on the web page. It needs the human feedback all the time to stay tuned, to be smart, to seem like it's intelligent, all right? So a lot of work really goes on in figuring out how machines work with people. It's not really work that goes on to figuring out how machines exist on their own or do something on their own. It really is, what are the boundaries of like how people work, and how can machines work with people in that way, okay? Here is an example of a machine that's doing something. It happens to be my car. And I'm driving home. It's a Tesla, so it's basically on autopilot. This little blue dot right here tells you that it's driving by itself, and it's going 70 miles an hour. This thing here, if you can read it, says the speed limit is 65. Apparently I can drive 112 miles before the gas runs out. You can see the temperature. Basically, that's a normal dashboard. And the reason why I'm showing you this is I want to explain, you think self-driving is simply a matter of getting an algorithm to stay in the lane or something like that, right? That would be a simple version of it. But what actually is going on when you're driving is there's a lot of people communication. So for example, when someone is driving next to you, sometimes they want to get into your lane, right? And so they might go ahead, and then they're kind of moving in a spot where they look like they might get into the lane, or they might actually look at you, with eye, and you're like, oh, okay, I see you want to get into the lane, so you slow down a little bit, and then that person gets into the lane. Well, when your car is on autopilot, they can do that, and then they can look at you, and then your car's not going to slow down, and your car's not going to let them in the lane, and then they're going to become mad. They're like, oh, you're such a jerk. You're a bad person because you didn't let me in the lane. I looked at you and you didn't let me in the lane. And that's when I've thought before I should have a sign that I can pick up and hold it out and then say, I'm not driving. Yeah. Both hands, look, I'm not driving. It's not me that didn't let you in the lane. It's the car, all right? And it's kind of getting to the point that just because the machine can by itself read the road signs doesn't mean the machine can operate well with people, and that's really what you want to happen. So, when will the machine be able to say, oh, that car is in a spot where it might want to get into this lane, maybe I need to slow down, or I need to communicate with it somehow. All of this has not been figured out yet. And this is an example of what I mean by this human to computer interface, that we don't have it yet, and people work on these things as research projects. So, there's projects where the car has a camera and it's looking at your eyes, and it can tell whether you're looking at the road or you're looking somewhere else. It can tell if it's getting your signals. It's also looking at the cars around. It's possibly seeing an accident that could happen but hasn't happened, whether you're paying attention to it. All of this is all to be learned, all right? And so that's kind of like the future of, where some of this artificial intelligence, at least in this application, would be. I could do the same thing with, human and robot interaction. So, for example, if you stand in a certain spot, are you about to then put your hand on the table? And if you are about to put your hand on the table, could the robot know that there's a chance you might do it and change what it's allowed to do, so that it's not going to put its arm right on top of yours or hurt you in some way? So all of this, getting the robot to be more aware of what the human would want or might accidentally do, is part of what people study when they look at artificial intelligence and things like that. Okay, and obviously we can talk more about all the things that are going in artificial intelligence. But this is a reasonable cross section. You can see a number of ideas here. Okay, so now let me switch to the job loss topic. All right, so you see all this stuff is going on. Machines can do things that seem like they're human. They're not human. They don't have any interest. They don't have any will, desire. They don't actually have any intelligence. But just artificially, they seem to do things that have human capabilities. Or they can do work that you think only humans could have done before, right? That's a topic or whatever. And so people are studying this. People are saying, well, what's going to happen? There are pessimistic people and optimistic people in this camp. One of the more pessimistic people are these people in England who wrote this study. And they say, oh, well, you know what? Maybe about half the jobs that exist in the whole world can be replaced in the near future. Right? That would definitely be pessimistic. And what they're saying is that there are things that are manually routine. Like if you pick something up and keep putting it in one spot, it's manual and it's routine. You do it over and over and over. That went away a long time ago. That could be replaced by a machine. But what if you're doing something mental, cognitive, but it's still routine? You're doing the same thing over and over, but just in your mind. You're like, okay, it's the same thing. Every time this happens, I do that. You're not learning something new. You're not figuring things out. You don't have a lot of variance in what you're doing. It's routine cognitive. They're saying even that can be replaced. The things that are harder to replace are where something new has to be done all the time, right? Okay, but there's a lot of these jobs which they're mental, but actually they're routine, right? So they used this approach and they said, all right, we see all of that declining. All right. If you want someone even more pessimistic, there's the World Economic Forum. And they say, oh, well, we could lose 7.1 million jobs in the course of this changeover. And a lot of them are office workers and so forth. And that would be partially offset by 2.1 million new jobs created that don't exist yet. But the net is still a 5 million job loss. All right, and they put this all under this term, Fourth Industrial Revolution. How many how many people will lose their jobs in this transition to what they consider the next industrial revolution. But there's another side of this story, and that is, and fortunately it's a more optimistic side. And so if you look back at history, every time that we had a situation in a previous version of an industrial revolution where a lot of jobs would be lost, in the end, we did not actually have that happen. All right? So I'll give you these examples. One is textiles. So textile manufacturing went from being done by hand to being done by machine, right? And in that process, when it was done by machine, for every 100 people, you only needed 2 to make the same amount of fabric. So you would have 100 people and they're doing it by hand. You replace them all with 1 machine and 2 people, and you can produce the same amount of fabric, all right? So everyone said, well, we're going to basically lose, and this is basically England at the time, in London, we're going to basically lose, our entire economy because just a few machines are going to replace all the workers. But what happened is that at that time, people had about 3 pairs of clothes, 3 sets of clothes. They had one that you wear, like on a Monday, and then you bring it home and it gets washed. And then you have another set that you wear on Tuesday. And then while that one is, by then, the first one is ready to wear again. And so 2 clothes would alternate you through the whole week. And then the one day, which is your holiday, whatever day it is that's off, then you've got the one special set of clothes that you wear on that day. So everyone basically has 3 sets of clothes, right? Okay. Once you had this very inexpensive way to make fabric, well, how many clothes do you have now, right? I'm going to guess that it's more than 3, All right, it's like most people I know have closets full of clothes. Most of them they don't wear at all or ever. Just put more clothes in that closet, right? So what happened is the global demand for fabric went up way more than 50 times. And so the net effect on employment was actually a 4x increase in employment, even though the machines had now come in, right? So no one ever knows. Right? This is why it's an open question. But it's not simply a story of, well, this many jobs will be replaced by a fewer number and that you lose them all. You don't fully understand what the new economics allow to happen because of it. Okay. The second example is, the transition from a horse pulling people for transportation to a car, pulling people, moving people around. And the same kind of argument was made. How many people have jobs where they have to somehow feed the horse, or they have to take care of animals, or whatever. There's a whole bunch of horse-related jobs. Okay, and what happened in this transition is that once people were able to drive, they were able to drive farther away than when they only had the horse. In fact, they could take people with them. So an entire industry came up around hotels that did not really exist before. Because now you could drive farther and you could stay somewhere. And while you were there, you would basically go to restaurants or you would do other things. And so, we lost all of the, quote, animal-related transportation jobs, but then a whole new industry sector was created around tourism, right? Okay, so in each of these cases, and I can say the same thing on the banking one, they said, every bank used to have 20 employees. Once ATMs come, you won't need so many, so they would reduce number. But in the end, the banks ended up hiring more people, even though ATMs got widely adopted. Okay, so in each case so far that we've seen, we didn't actually have this issue. Now, will AI be the one that was different? is AI so much more pervasive than all the other transitions that we have? We don't know yet, okay? Like, that's why some people believe one way and some people believe the other. But it's not a simple matter of because you lose a job, that job is just gone. It's like we don't know all the other economic factors that are caused by it. This slide just basically says half the studies are pessimistic and the other half of the studies are very optimistic, like that. Transition effects are still a factor, and basically, the thing is that you may have a lot of economic growth, but it probably starts with some loss. And how long is that loss before the growth happens? This is something everyone's got to be concerned about. All right. So just pointing that out. Okay. So I'm kind of getting to the end of this part, and we can talk about all of these things. But let me kind of take you through this argument, right? And the argument is, if you were in the last industrial revolution, okay, what are your choices? Choice one, you could say, well, I'm going to decide not to participate. Like, we make shoes by hand. We're just going to keep making shoes by hand. Doesn't matter what everybody else in the world does. We're just going to do it the way we've always been doing. Is that a reasonable, looking back, is that a reasonable approach? Obviously not, right? Doesn't matter how hard you work or how good of a shoemaker you are, you cannot beat the machine once the factory line is installed. Just impossible, right? So if you look back at the last industrial revolution, the people who created the tools, the machines, they did fine. The people who learned to operate the machines, they did fine. The people who learned to design where the machine flow fits into the work environment, they did fine. The people who suffered are the ones who basically said, I'm going to keep doing it the way I'm doing it, and we're basically competing against the machine. So like, you're basically in a much better position if your point of view is, I'm going to learn to operate one of the machines or use it somehow. You're in a worse position if you decide that you want to be competing with it. Okay, so, somehow, I think you can translate some advice, from that. Okay. Now, the other thing that I would say is that I'll just bring it back to the psychology topic, right? So, innovative people with entrepreneurial behaviors are the best people to survive these transitions. So whenever there's a transition, there's a group of people that will say, this is the way I've been trained, this is what I've done for some number of years, I'm not able to do any other thing. They believe it in their head, that that's the only thing they can do. The problem of they believe it in their head, that that's the only thing they can do, is a bigger problem than whatever knowledge you can distribute. It's not a matter of, can we teach people other things? It's not a matter of, are all those resources available? The biggest inertia will be the person who just doesn't believe they can do another thing. And then they get stuck, mentally they get stuck in that spot. So yes, training and retraining, that's a very common topic when people talk about how will the economy change and how will people, be taught to be part of a new economy. But I think the much bigger issue is, what's the psychology that you're starting with? So if you got the psychology that basically makes you entrepreneurial, that broad version that I brought up in, when I started the talk, we think that's fundamental. We think people can figure out how to adapt in all kinds of situations if they want to. If they are trained not on the technical topic, if they're trained on the psychological topic of how to be adaptive and how to have wide comfort zones, how to, survive in changing environments. Okay, so those are my, I guess, points for the talk. I am, hopefully that was, at least at some level, interesting. And I'm open for questions at this point. Yeah, okay, go ahead. Okay, where is the mic? Okay, oh, they all have it, okay.
My name is Dr. Fouad Al-Kout. I'm a proud graduate of RIT Rochester, New York, and University of Surrey, CVSSP. I was wondering, besides establishing the center, you're probably still working on some kind of research. I mean, I was wondering what is the area that you're working on in machine learning, if you are still investigating. Okay. And I noticed you had in your list one option, one of the projects was autism detection.
Oh, okay.
Where did you reach on that one?
Okay.
I had a paper in 2016 where we found a solution, a marvelous solution, but we used some classifiers and then combiners, but we had to reduce the features because of the chromosomes. 60,000, we reduced them to 500, and then we got a good result. Finally, when do you think, I mean, machine learning will replace many jobs.
Yeah.
It depends on your data. You have data, we have machine learning solution for it. If the Tesla is not doing perfectly, it's because it's the beginning. It will be there. Jobs will alternate, will shift to other areas. So some jobs will be lost, and new jobs will be created. My question is, final question. What do you expect to be the next breakthrough in machine learning? I mean, now we have classifiers, we have combiners, we have fusion methods, we have feature selection methods. All of these scientists are playing with, trying to perfect them. But, for example, everything has to be parameterized. You have to have features to be able to build a machine learning system. For example, emotions, when will you have a machine learning system that can mimic human emotions? For example, I'm just saying, what is the next breakthrough in machine learning?
Okay, all right. Let me see if I can remember all your questions to answer them. But yeah, I can. All right. So question one, what research project am I working on related to this? And I know autism and then breakthrough. So the answer to the first one, one of my most favorite research projects right now is something which we call Berkeley Innovation Index. And what we've been doing is we've been trying to understand the psychology of people and translate that into metrics. And what we can try to figure out is by asking people certain questions, we try to figure out which parts of what part of the way they think, how does that support being innovative? How does it support being entrepreneurial? What are the factors deeper down that you could measure their innovation capability, or like at an individual level, like basically measure their psychology towards innovation, towards entrepreneurship, things like this. And then we've been extending that, and we're saying, okay, if we take it for like 100 people that work together, what could we figure out about how that company should be like best organized, which people might work well together, what information do these people have that they might not be sharing, or who they might not be sharing it with. There's a lot of organizational information that we can also figure out or translate from this. And we're using machine learning on the back end to find signal out of these psychology tests. That's basically the research project. Okay, so I'm trying to think, should I leave it there or not? But just, let me do that. Let me say, like, that's an example of a research project. I will say, like, we're experimenting with many other things. We're working on, like, machine learning applied to telecom. We're thinking about new blockchain protocols. I mean, like, it's not the only thing, okay? But that's definitely a project where we have a lot of momentum and time that we've put into it. Autism detection. This is actually a student-run project that you're talking about. And what they said was they had found some study that says that that at a very early age, there are things that you can look for in the child, and they are indicators of whether the child will be autistic or not. And it has to do with like their gaze or certain, like how they react to certain things. And the earlier that you can catch it, the more likely that you can improve it or treat it. So their goal was, what could we do so that parents could be asked certain questions that they could fill in to like a web app or like a mobile app, and with some basic data, some really simple data, to be able to tell them that, you know, you should actually have some treatment done, or you should actually get this looked at. So that was actually what that project was about, okay? And I'll say, like, I heard your point about results that you have, and that's great.
We use a blood sample, even if the signs are not visible, because the waiting list to see a doctor, a professional, to detect autism is a long list. So we just use a blood sample, chromosomes, and from that we have reached 100% detection. We started at 62%, and our accuracy reached.
That sounds great. I should connect you with them. Yeah. Okay.
The paper is there, 2016.
Yeah, pretty recent too. Okay. And then the third question is maybe like, what's happening? What do I think is the next breakthrough? That's a really hard question. I could show you a list of many research areas that are going on, from different kinds of computing platforms to whoops, there's nothing back here. Let's see, breakthrough. Yeah.
It doesn't have to be an engineering answer, It's what you feel.
Yeah, I actually feel that there's almost a little bit of hype with machine learning and artificial intelligence right now. I think there's a lot of technologies that we have developed already that are not getting properly looked at, or people have kind of forgotten that some of these other things are so like useful and valuable. So on one hand, I'll say I don't know that a breakthrough is really the thing that is necessary here. Yeah, I'm going to take another question. Let me think. If I think of what I really feel is a good answer, I'll come back and I'll tell you. Like, I'll tell you in front of everyone. But
thank you.
But let me think about it. Yeah.
Hi, Fel Smith from the Gulf University for Science and Technology.
Yeah.
I appreciate what you're saying about the individual psychology and how that plays into things, but I'd like to ask you to talk a little bit more about the sociology. And the pace of change is something that's unprecedented, and this raises the question of how much do you try and harness and control this versus how much you leave toward innovation. And I'd like to hear your ideas about what are the roles of, say, regulation and ethics and rules for these kind of things versus allowing sort of a more free market approach to innovation. Where's that balance going to be struck? Because the stakes are higher here in many ways than they've been before, and the pace is faster.
Yeah, that's a really good question. So the way I think about this is that if you don't have any regulation, okay, you will basically do well from an industry point of view. You'll lose more jobs and you'll lose them more quickly. And then the people who lose their jobs will become increasingly upset, and they will put a lot of pressure in that local area and all the people who are, quote, running the place now. So you get this trade-off between the economic situation and the social tension. in the other end of the extreme, let's say the policies are set up to be very protective of the people, then you'll have people basically comfortable for a much longer period of time, but regionally you lose competitiveness with all the other regions that did not have those regulations. And so, what is a better situation? Do you want to be completely non-competitive some number of years in future, or do you, I think neither of the extremes is a good one. And what is going to happen everywhere is there's going to be some middle ground, there's going to be some tension, and the amount of policy that gets put in, like how quickly can you displace the jobs, how quickly can these changes happen, that's the role of policy. And I think you're going to find there's a middle state that everyone's going to have to negotiate in their own region, in their own country, in their own economics. Yeah. Okay. All right.
This is Hassan al-Bahrani. I like the slide at the beginning for the individual.
Yeah.
And you focused only on how the new business, how the new entrepreneur started, how successful they are. What is your research about how the existing organization to adopt the new technology or the breakthrough within the artificial lift intelligence system? I believe for any organization they have a competitive advantage where they have their own processes, structured, culture organization.
Yeah.
So how it impacts the strategy of existing organizations?
Yeah, okay. So you're basically saying if you're an existing company, like how do you adopt these things and what happens? And you're right, this is a multi-layer problem. It's partly culture in the company, it's partly the technology skills, it's the people skills, it's the strategy, it's the business environment. There's no 1-minute answer that I can give you that can cover all of these things. This is like, a 2-day discussion. But high level, I would say, there's business first and technology next. I'd say you have to understand your real environment and what's going on. Like you can't just say, here's a technology, I just want to somehow throw it into whatever is going on. I think you have to do business strategy before you do technology strategy. So that would be my first thing. But technology does lead to opportunities that you never would have been able to consider before. And so I'd say business first, then technology strategy. But while you're doing that, it enables another set of opportunities. And then we could go into what motivates people, how do you get out of inertia? There's alignment between the top and the rest of the company. There's a lot in the rest of that answer. Okay? Okay. Why don't you pick a person for me? Oh, yeah. Okay.
Dr. Faisal Obaid from Computer Science Department, PAT. First of all, welcome to Kuwait. I hope you're enjoying your stay.
Yeah. I'm gaining weight.
Oh,
I
the food
can
is
tell
good
you
here.
that right now.
Excellent.
Yeah. It's working.
Yeah. So my question is, you mentioned that AI as a helper for human, instead of taking the human out of the loop.
Right.
Do you subscribe to this idea universally? Or you see that some areas we can take the human out of the loop and it will be better? Let me give an example. You gave an example for your Tesla car. And you say, my car doesn't communicate with the human next door, so he cannot take my lane. But
say that one more time.
Yeah, your Tesla car cannot look at the human next in the next lane to understand that he wants to give way for him to take your lane.
Right.
But of course, we will get through a phase that our roads will be hybrid. Some driverless cars, some human-driven cars. But if you further in the future, if we have all driverless cars and they will communicate with each other and we take the human out of the loop, that would be better in this case and some other areas, of course. I'm talking, is it universal concept that no, don't take the human out of the loop, or some areas it's better to take the human out of the loop?
Okay, all right, fine. So first to your example, what you're talking about is a much farther off time period. There's a lot more interesting things that will happen in the interim between the first driverless car to the last human leaving the road, right? So that's a pretty long time span. But there's plenty of times when we've taken the human out of the loop, and it doesn't have to do with artificial intelligence. Like, we've automated a lot of things where somebody writes down a list of instructions one time. It doesn't change very often, so the machine just does that thing over and over and over. The question is, how much does the machine have to learn while it's doing something? And that's really where artificial intelligence is more relevant. And so I say if you're in a completely static situation, that's fine. But when you're in a dynamic situation, it's a lot. See, there's two neural networks in the world. There's the one that's in everyone's head, and there's the one that we're making in these machines. And if you just leave it to the ones in the machines, they're just much more at a disadvantage. So maybe they can figure out and learn something, but if they could actually watch what the human who has much more capability, they can pay attention to what the human does, they actually learn a lot faster. So I'd say even from an efficiency point of view, it's better to have the human in the loop. Yeah. Okay. Yes.
Thank you very much. This is Salim from KFAS.
Yeah.
I have two small questions.
Thanks
the first
for
one,
hosting.
Thank you. You are most welcome, and we are honored to have you with us.
Yeah.
The first question is, during the 90s and early 2000s, artificial intelligence is limited to the mathematics department's theories and probably the computer science. Nowadays, it became an application where almost every department in every university, they are using artificial intelligence. So in UC Berkeley, where your students usually study the artificial intelligence, are they getting it in every department they are studying in, or there is a specific department teaching these skills?
Okay.
The second question is, I'd like you to shed some light on the relationship between artificial intelligence and blockchain, mainly Bitcoins, and is there any strong link between the two technologies?
Yeah, okay, all right. Okay, two very good questions. So the first one, where are the students? So to me, first of all, I'll tell you the structure. So we have computer science as a department. People get PhDs, they study in this area, and they do it either in artificial intelligence or they do it in a more machine learning. Like there's multiple versions of artificial intelligence. There's the ones where you're trying to emulate what a human would do, and then there's the ones where you're just making smart decisions. Like to make a robot act like a human is a different field than making a machine that serves you for some other, not just serves you, but automatically does something. Like making a self-driving car is different than making a robot that talks like a human, right? Put it that way. So where are the students? Certainly we have students in computer science, and then we have a division of computer science. And the division of computer science is not in the College of Engineering, it's outside the College of Engineering. It reports in some very odd way, partly to the head of computer science and partly to the vice chancellor, researcher, provost. In other words, it's somewhat outside of the traditional computer science department. More to the point on the kind of like what students are doing. The way I think of it is there's kind of two versions of why you study this topic. One version is you want to make the tools of the future. So if you don't care about the application, what you care about is making that next statistical tool that would let you crunch much more data or would let you learn from data or whatever it is. You're not caring about the application, you're caring about the tool itself. And computer science has typically been where all the tools have come from. So at one time, Unix was developed. At one time, Spark was developed. There's a whole set of tools, and there will be more and more tools that will be developed. And you have to be really a specialist, like really, really understand this well. And and those people go eventually to all the research labs. They go to Google. They go to everywhere where people are making TensorFlow and all the future tools, right? There's another job that exists in the world, which is you bring a bit of your understanding of how to work with data into all the other applications in the world. So you're not so much a specialist in the making of the tool. You're a little bit more of, I know how to use some of the tools, but I'm a specialist in finance, in manufacturing, in other things, and you're bringing data and artificial intelligence and machine learning and the applications into those areas. So I say the answer is it's everywhere, but it depends on what people are doing. When they're really narrowly focused on the tools, they end up in computer science. But a lot of the new things that will happen will bring these tools into humanities. They'll bring it into medicine. They're going to bring it into all this other stuff. And for that, there's another set of students that are not computer science students. Yeah. Okay. Oh, your second question. Try to remember it now. Blockchain. Yeah. Okay. So these are like two incredibly hot topics right now. Blockchain and artificial intelligence. So on their own, everyone is talking about these things. There's lots of opportunity and lots of hype in some ways on both of these things. And now you're saying, what's the intersection of these two things? The thing that comes to my mind is that blockchain allows a rate of transaction automation that we've never seen before. And right now it's not scalable in that way, but the more that you have smart contracts, the more that you have an algorithm making decisions on everyone's behalf, and all these things are happening, now I see another problem, which is how do you know when the machine did something that is not something you would have wanted it to do? What audits that? What keeps track of all that? What knows that this is statistically different than what you would have expected? Because you don't have time to watch all the decisions that the machine is making. So I think that's certainly one area where you're going to see artificial intelligence and this high-speed volume of transactions that are happening all the time. I think that's one thing. If you give me some time, I could probably come up with more. Yeah. Okay. All right. Last question.
Professor, you mentioned about redesigning the data science class over the period of 2 years, and you scaled up from 55 to 220.
That's right.
And it will be grateful for us. We can learn a lot from what are the priorities we need to have, and what are the issues we need to address to redesign the whole approach, to kickstart and then scale up the whole operation.
Sure. So first, I should say all of our materials are publicly available. There's a website. It's called data-x.blog. All the code samples, videos, slides, they're all there, and we're adding new things all the time. All right. And I'll just make my answer short, for time. But I think the most effective thing that we did is we reordered everything to serve the project. So if it was a beautiful theory, but it doesn't help in making the project work, we delay that or we don't have it. And if something is less exciting as a theory, but you really need it to understand how to make a function call that you need for most projects, then we'll explain it, and only what you need. So we basically took a very practical approach to the teaching of it, and we used the project as our lens to know if it was truly practical or not. Okay. All right? Okay, with that, thank you all. Yeah.
Thank you, everyone. Time to go eat again.
Yeah. Gain some more weight. Okay. Yeah. Okay, thanks.